Okay, can I have everybody's attention? Today I want to introduce our speaker to you. This is Rafael de la Torre. And one thing I got to say about this talk is, out of all the talks we've had all semester, this is the one that I'm most excited about. And the reason why is because Rafael is just not somebody who we just kind of pulled in off the street to give a talk here on physics. This is one of our alumni from our physics department. And he actually did the project that he's going to be talking about as part of his capstone work for the master's degree in physics. And, you know, some people ask the question about whether or not you should do the capstone or whether or not you should do a thesis. And Rafael is one of the people that did the capstone. And so what he did was he basically, we're working on a project where I was looking at gravitational waves from the early universe. And Rafael kind of took this and we were looking at, well, what happens with these quantum mechanical effects and how would this affect the spectrum of these gravitational waves. Really interesting stuff, which he'll go more in detail on. And he came out with a really nice piece of work where he actually wrote a program which can calculate the spectrum of these gravitational waves with or without these quantum gravity effects or string theory effects, and can do it for pretty much any part of the history of the universe. And so he finished this, presented it as a capstone project, and then afterwards we did a little bit more work on it. And in January 2008, this was published in Classical and Quantum Gravity, which is, really good, high-quality journal. And because of the fact he wrote it up very well during his capstone course, he was able to just transition it from there. So I guess with that, I'll turn it over to Rafael.
All right. As you see, the title is Numerical Analysis of Simplified Relic-Birefringent Gravity Waves. It's a long title, but I hope through this presentation I'll give you a clearer understanding of what all that long title means. So we'll start at the beginning, because it's good to understand this as we get into the research we're doing. Obviously, many of us know that the standard model of the universe, Big Bang, it's originally discovered by Edwin Hubble as he was observing distant galaxies. And everywhere he looked, he saw a redshift. And that redshift translated to these galaxies accelerating away from us. There was a lot of talk before that time between a steady state universe and a Big Bang universe, or hot Big Bang. That's where the term came from. And what Edwin Hubble found supported the Big Bang part. And as many of us know, there's been decades of supporting evidence, confirmation of Hubble's observations from various sources, and then relatively recently, in the last 20 years, the finding of the cosmic microwave background radiation. That was very key, one of the defining observations for the Big Bang. Even now, I don't know if many of you saw in the news, there was a discovery by the Hubble Space Telescope. They observed 500,000 galaxies and confirmed this observation as well, that the galaxies were all redshifted. So there's our standard model, and we're going to spend most of our time talking about this area right here. And we are way over here, 13.7 billion years later. But with your standard model, there's some basic components. Let's focus here for a second. This is what you see in the cosmic microwave background. The surface of last scattering is what it's called. And then there's some dark ages, and then after this point, or actually beginning with these dark ages, is when we change from a radiation-dominated universe to a matter-dominated universe. We'll spend a little more time there. Now, with the Big Bang comes big problems. If you just go with the standard model itself, there are three problems that arise that are related to the research we're talking about. The first bullet I have here is really related to two problems, but they have a similar solution, which you'll see in a second. The problems are called the horizon problem and smoothness problem. So when you look here, this is from the WMAP satellite. This is looking at the background radiation in the universe. Some of you have probably heard of this background radiation. And basically, it's predicted with the Big Bang, and as a prediction show, we should have somewhere in the neighborhood of 3 Kelvin temperature all around the universe, all across, and it shows it. Now the problem with the standard model, when you don't include things like inflation, or if you evolve these backwards, what happens is you have parts of the universe that are separated by billions of light years or millions of light years that are at the same temperature. And they couldn't have been that way if they were expanding at the speed of light. It would have taken many years, or they would have had to have been different temperatures that we see. But those differences that we see here are very, very small, in the thousandths of degree, very, very small differences. So that's one problem with the Big Bang model. The other is when we look at the smoothness, in other words, the clumps of matter that we have in the universe, if you take those backwards in the time, the primordial matter must have been very, very smooth, almost absolutely smooth. If not, we would have very distinct local areas of gravity in the universe, and then areas that were not homogeneous. So there's two problems with that. The bottom one here is also an interesting problem. It's called the flatness problem. Observations by WMAP and COBE and other satellites show that the universe is pretty much flat as far as shape, and that also does relate to the matter in the universe. These shapes here, if you look at these, this is the density ratio, and so the critical density here is where the actual density of matter in the universe compared to the critical density is 1. It means basically it's geometrically flat. If we're less than that value, then we're hyperbolic, or hypersphere, excuse me. And here, this is the hypersphere. And this one here is saddle shape, if we're less or greater than 1 on the constant. So again, what I have here, these are curves that, if you take that density ratio and evolve it backwards, you would have had to have that value be 1.0 all the way to 15, 20 decimal places, basically staying very close to flat, which then would not correlate well with the observations that we see. If you take that almost flat universe and extrapolate it out for 13 billion years, you're going to get a lot more than what we see today. So, in comes Alan Guth. In 1980, he developed a theory called inflation theory. And basically what this is it solves many of the problems, and all it is a very rapid expansion of the universe at a very early time in the beginning of the universe. We're talking in 10 to the minus 35 to 10 to the minus 32 time frame. Very small. What this does is it solves the horizon and smoothness problems by expanding not necessarily the matter in the universe, but the space-time where the matter or the radiation at this point is contained. So it expands that a lot faster than the speed of light. That allows everything that is in thermal equilibrium to expand with the universe, and that's why we see it as we do today. Same with the smoothness. You can have smooth matter in there, and then it expanded so fast, and that explains why there's not as much clumping as we'd expect. The flatness problem is also very interesting. I found this picture online, and that's very nice. It's an ant standing on a very small sphere, let's say before inflation. There's curvature to the universe at that point. But if you provide an exponential expansion out here, now it's relatively flat to that ant at that point. So that explains the flatness problem. Now, inflation theory is nice, but again, it is a theory. And although it solves some of the problems from the standard model of the Big Bang, it also introduces some new exotic things like quantum gravity. The cosmological constant also gets revisited. Einstein thought it was his biggest blunder, but it really wasn't. It was something that the inflation theory needs to deal with the vacuum energy at that point. So these exotic things, not many people are too comfortable with them at this point. They're very tough to prove. Nevertheless, it's exciting. All right, let's take a step aside for a second. We've talked about inflation, and again, we're setting this background up to get into the main talk here. But gravity waves, or gravitational waves. As many people know, it's a prediction of Einstein's general relativity. And if you have mass anywhere in space-time, it curves at space-time, and his equations show that. And then the larger the mass, the greater the curvature. I'm sure you've seen many of the programs where you have a black hole in the middle of space-time and very deep gravity well. And these result from Einstein's equations being written as wave equations. So the point here that helps us is that very large mass-energy objects in motion create ripples in space-time, and these ripples are gravity waves. So possible sources include black holes and massive dense stars, and of course what we're interested in, the very early universe. So here comes the first part of that title, relic gravity waves. They're basically remnants of the exponential inflation of the very early universe. Here is a hypersphere, four-dimensional sphere, including time. And so you see, as this is a model. I can't quote the source right now, but I know it's in the paper. But as this sphere expands exponentially, it creates ripples in space-time. And so the theory there is that those gravity waves should be detectable today. And I'll get a little more into that. All right, and just for grins, this is a spectrum, a gravity wave spectrum. This is perhaps an analog to the electromagnetic spectrum, if you will. Here on this side is the area we're really interested in. These are quantum fluctuation of gravity waves that could have been produced. The thing to point out here is the frequency. The frequencies here, 10 to the minus 16th, 10 to the minus 14th, and so on. And then there are certain probes, which I'm going to get into in a little bit, or certain methods to try and detect these frequencies. But the ranges we'll be looking at, as you'll see, are either very small, or I could believe it's in here where you can use pulsar timing as well to find these waves. And then other experiments, LISA and LIGO, which are looking at more realistic or more observable frequencies. Just a nice little chart in there related to electromagnetism. All right. So these relic gravity waves. The reason why they're so important, or the reason why we want to find this, is that they're possibly associated with cosmological structure formation. Leptogenesis, basically the generation of matter, or the seeds of matter, the quarks, everything that eventually turned into matter. And then in support of Dr. Garrison's research, GRMHD, turbulence. If you have a plasma and you introduce gravity waves, what happens? Does it create matter? Does it cause the asymmetry we see in matter and antimatter? These are very important things to research. A gentleman by the name of L.P. Grischuk is pretty much the founder of relic gravity wave theory. He's done a ton of papers on this. And then recently, Stefan Alexander and several other authors put a little twist to this work that he did. Basically, they introduced quantum gravity effects. Now, as many know, there is no recognized theory of quantum gravity, no theory of it. But there are several effects that are assumed to be part of it. Some of them string theory, loop quantum gravity, and other things. So, some of these terms were included, and what they predict are very small anisotropies in space-time during the early universe. Very, very small, hard to observe. Probably, if I can go back a slide or two, probably on the order of these. I mean, these probably are due mostly to the anisotropies that show up. And they are quantum effects, which is very big. It would tie quantum mechanics to gravity, which is something that till this time hasn't been done. So the theory here is that these anisotropies produce birefringent gravity waves with different polarities. So think of it this way: if you shine a light ray through some substance and it's not isotropic, it's going to create birefringent. It's going to split the ray up into two, and you'll have two different polarities. And that's the theory here. Is that here you have, for this one, what we call the cross polarization, which this is a ring of particles, and so it will travel either this way or this way, as you'll see it. So that's the way that ring will work. And then this one over here is, well, this is plus, this is cross. This is like an X. You'll see it travel this way and then this way. And what basically this does is in the paper by Alexander, Martin, and others, they take this polarity and switch it and turn it into left-handed and right-handed polarities, as you'll see. So, very big and interesting theory. So now getting back to relic gravity waves. The theory suggests that the same way there's a cosmic microwave background, there should be a cosmic gravity wave background. There should be gravity waves permeating the universe. You just got to find the right detector, point it at it, and find it, just like you do with the CRB. And what I have here are some proposed concepts. This is LISA. This is basically 3 satellites put in deep space at a very far distance from each other. If there are ripples in space-time, the satellites will move slightly, and that changes the highly calibrated distance between them, which may indicate a gravity wave of some sort. Here on the bottom right is pulsar timing. Pulsars are very predictable, very accurate. The timing is pretty much has been put down and is recognized very well. So if you have a gravity wave coming through here and it upsets that timing, you know something is coming through there. Now, the detection of relic gravity waves would go a long way towards helping support the theory of inflation. But then detecting these birefringent gravity waves would provide evidence of quantum gravity effects in cosmology, which is something many people have gone and tried to look for. Definitely another step closer to grand unified theory. Now, what you need for these instruments is you have to tell it what to look for. You have to tell it what amplitudes, what frequencies. Back on that other slide, I was pointing out the frequencies that you saw across there. So we need to come up with that, and that's done theoretically. So, of course, you can't have a theoretical physics discussion without equations. So, we have relic gravity waves, and they basically result in tensor perturbations. Of course, there's 3 types of perturbations to the Friedmann-Robertson-Walker metric. And so basically, this is the tensor perturbation here. There's scalar and vector are the other ones. And then here, this is the same metric, just turned in terms of what we call conformal time, which is just easier to use in these equations and theoretical equations. And it's related to the scale factor of the universe and cosmic time. So basically, this is where Alexander and folks do their magic. They say that these tensor perturbations, they use them as operators in quantum gravitational expectation function. So here's our expectation function, and here's the tensor and its conjugate, and they put it in here to determine expectation function. And then they take the mean square amplitude of that spectrum, and that's going to be what we solve. We'll find that number, and that'll tell us the amplitudes we're looking at. The big key to that is this mode function. As you'll see in a second, this is the part that becomes pretty nasty theoretically, but it is solvable at least numerically. So, getting into this mode function. Basically, it's composed of the gravity wave equation, which is this guy here. The subscript P indicates polarity, so if you have a left-handed or right-handed wave, this function will change. I think it's more in sign or in value because of the sign changing inside the equation, and I'll get to that. And notice they're all functions of conformal time. This one here is called an effective scale factor, and the effective scale factor and the gravity equation are coming in the next 2 bullets. The scale factor and effective scale factor have the following form during inflation. So here's our scale factor, and then this here is a reference length somewhere in inflation. It's a little bit bigger than Planck length, just during inflation time. Beta here is a term that relates to related to the cosmological constant. Basically gets into what we call the Sitter universe, which is a no-matter universe, or relates to it. It'll relate to it, and it actually has been observed by WMAP, and it's been a little less than that value, but theoretically it exists. The effective scale factor here is just the scale factor times some gain. And what I'll point out here is here, this lambda p is just the polarity sign. It's either plus or minus, so that parameter doesn't grow or change too much. The theta parameter, or theta kn, really, or k eta. This term here is really key, and you'll see in the next step how it helps in the simplification. This is where I believe a lot of the tuning for looking at these spectrum in the future, this is where a lot of it's going to take place, is in trying to find these values right here. Theta is your birefringence parameter. It tells you how anisotropic the primordial plasma or quantum fluctuation state was. So if you set that to 0, it vanishes and your effective scale factor is the same as your regular scale factor. K is our wave number, which spans across the different lengths as we grow with the universe. And then 8 is our conformal time. And I'll show you in a little bit how we use that to our advantage for this study. Now the gravity wave itself, that's another one. That's it's key to determine the mode function, and you can use a simplification and show that it's given by the equation of a 1D harmonic oscillator. Very interesting. Of course, with these equations, the big thing that drives that equation is this effective potential. Whatever form that has will dictate what your solution to this differential equation is. That's very similar to quantum mechanics. So, here on the left, this is standard gravity waves with no polarity, no birefringence, if you will. So you have here, this is what we call our effective potential. And it's the simple form here, where you know, after some simplification and reduction here. And so our general analytical solution is pretty much composed of Bessel functions with a few constants and the other terms outside. Whereas here we get into the birefringent gravity waves. Up here, this is our effective potential for the general solution. And as you can see, that's going to probably be very difficult to solve analytically. And up to this point, I don't think anyone has solved it analytically. And we cut our losses and determined to go with the simplified form the first time. And so we did that by using that combination I was pointing out earlier, K, theta, eta, and setting it a lot smaller than 1. And what that does is it removes some of these terms from the denominator and simplifies that effective potential, which is still not as easy to work with, but it's better than what we had. There do exist solutions for that differential equation that you saw on the previous page with that effective potential, and this is the solution. These are hypergeometric functions, basically the Whittaker functions is what they're called. This solution here, again, it gets pretty complex with pen and paper, but as you can see numerically, it's a little simpler to solve. Some observations here. The good news is for all of these equations, which made us feel good as we went through and developed this and reviewed the theory, is that if you set theta to 0, this will simplify to these Bessel functions, which is that birefringence term. And then they all behave the same. If you set the wave number to be much smaller than the effective potential, it just behaves pretty much as a function of the scale factor. And if it's much higher, it behaves like a wave, if you will. There's some simplifications there. All right, so the theory part is out of the way. So now let's talk about how we apply this. So we have a spectral amplitude and inflation, and that spectral amplitude is redshifted as the universe expands. Just like the microwave background, it was at a much higher temperature, and as the universe expands, it's in the microwave range or radio range, and the temperature shifted with it. So this method here that was developed by Grischuk, the gentleman that developed the original inflationary gravity wave theory. And basically he put a method together where you can make this redshift a function of just the scale factors, the ratios of them. And as you can see, there's some breakpoints. And inflation is where we start. And here in this reheating phase, once inflation was over and things started to combine again, the wave numbers, as you can see, the ratio of them is equal to the ratio of those scale factors. And so you just combine those. Then during our radiation-dominated era, we have another combination. And then finally, for the matter-dominated, where we are now, we have this combination. So this goes back to what Dr. Garrison was talking about, where, of course, we're going to look at this right now to see if we can find it. But going back to where his area of research, which I remember was 3 minutes after the universe started, you can go back in here somewhere and then redshift it to the value you need to apply into his code. So, very interesting theory here to check out, and you can check it out at many different times. You don't just have to look now. One more item before we get into the numerical discussion. One of the interesting things is as we set this up, we had to start looking at the parameters that were going into the numerical solution. And that actually gives you an indication of the way some of the parameters that they're finding in the universe are matching up with things, or maybe perhaps some limitations that may be involved, as I'll go through here. First and foremost, the frequency range, I mean, that's typical. Pretty much the whole gamut of what you can see. The low frequency limit corresponds to wavelengths, which are greater than the current Hubble radius. And then the high frequency relationship is established by this relationship here, the ratio of the Planck length to that reference length I told you guys about inflation. And then the frequencies there, and this B parameter, which is related to beta. So as long as that is less than 1, that's the upper limit. Then the beta parameter, which I mentioned earlier, which is that power law expansion parameter, has to be somewhere between -2 and -1.9. Now what that does is it, -2, again, remember, that's the de Sitter universe. That's no matter in the universe. It's an ideal solution to Einstein's equations. And the 1.9 actually comes from observations from WMAP, which they support that the density of the matter to the universe is very small. His approximation is pretty close, is what it says. So that was very interesting to see. And the work by Grischuk also uses this, so I believe somewhere along the line they found this answer as well. And then the theoretical restriction here was found by confirming it by using this. Now this birefringence parameter, we stopped with this value, just 1 times 10 to the -5. And this parameter is constructed of quantum gravity and string theory assumptions. Values greater than this result in a nonlinear effective potential. So to save ourselves a lot of work at this point, we just wanted to look at the basic behavior of this being very close to the regular, standard relic gravity wave. So we set this parameter pretty small. And then our conformal time just falls out of that other relationship I told you guys about earlier, which is k eta theta being much less than 1. So again, this gives us a little insight into some of the properties of the universe that these equations are telling us exist. So the approach, it was actually interesting. We went searching and started looking through a lot of these equations, and it turns out, when you look through MATLAB, they have a lot of what we needed. All we had to do was modify it to apply it to our needs. But of course, their built-in Bessel and gamma functions are numerical. And then there were some functions online that gave us the pieces we needed to put together. They came up with these Coulomb and gamma functions that were developed in the user community. People were just making these. And so we went and got those, found them, put them together, made them start working. Of course, tweaked them to what we needed. And what we did was we just evolved that particular solution using the variable constraints I just described on the last page. And then when we went from there, we calculated that mode function and the spectrum at some initial conformal time. And then from there, you redshift it to whatever time you need using Grischuk's method. Again, we can stop at 3 minutes, we can go now, we can go forever, and see what it all is going to look like. We plotted the resulting spectrum and differences between models. We looked at all that. We wanted to compare it to the standard model, which is our validity check here. We set that theta parameter, which measures birefringence, to 0. And we wanted to see if it matched the standard model, which you'll see it does in the next chart. And we compared the results to theoretical approximations. So, this is what we found. So here we have the standard models for beta equals -2 and -1.9. And then over those, if you can see there's a blue line and an orangish line there. They're over these dashed lines, and those are the theoretical values we came up with using the numerical analysis. As you can see here, these are the differences in them, which some might say, how can you even tell that difference numerically? some might say if they are accurate, that they'd probably be very difficult to observe using a detector to discern them between regular gravity waves or standard relic gravity waves. And here are some comparisons of where these methods for detecting these gravity waves are going to be, in what frequency ranges we're looking at. And so here's the pulsar timing, and then space-based LISA, and then the ground-based LIGO, which they have these detectors out there, I forgot where, Virginia or Washington?
Hanford, Washington.
Washington.
Livingston, Louisiana.
And so these guys are all, this one's up and operational already, and it's looking for gravity waves now. This one is planned, and then this has existed for some time, but they have not found anything conclusive as of yet. So what this chart tells me basically is that when you simplify this and you keep that birefringence parameter small, you get what you should get, which is the standard model. But what that also tells us is that we have a place to start building upon, to start changing those parameters and look to see if by changing birefringence and other things, if this spectrum starts to shift anyway, which may help these detectors or also point other detectors in the right way. And I think I covered that. So I mentioned this first part already, I won't go over that. But again, this is the main thing, and this is the parameter where any future research in this area should focus on, is that relationship right there, that birefringence term, and then the wave number and conformal time. If they were created, if these birefringent waves were created, they may not be distinguishable unless these values are different, which, as I mentioned already. Another thing is that we can imply a limit based on the general solution, looking at the equations, at least for the right-handed waves, that this parameter here, or this combination here, has to be less than 0.5, and then this conformal time has to be less than 5 times 10 to the minus 15th. And there's a detailed explanation in the report for that. So when I left, and unfortunately until this time, since I haven't had a chance to work on this, here's the forward work that we had back then, and we still have. There was a paper written by Zhang et al. They proposed to incorporate, if you remember, I go back, whoops, go back a few slides, or up a few slides. This spectrum right here, or the redshift right here, they put in another accelerating universe segment in there. And so they proposed going in and updating the spectrum for that. So that's one thing that needed to be done. Another item is examine a numerical solution for the general birefringent ODE, and then look at that nonlinear behavior to see what changing that birefringence does to that spectrum. That would be very interesting work. Also, to support Dr. Garrison's work, look at that spectrum at 3 minutes, target the redshift for this period, and then see if this has more implications. Perhaps it's not observable at this time, but maybe it has implications on what it did to the plasma back then, which may support the discussion on how matter became to become evident. And then finally, take those algorithms in MATLAB and transport them into C++ and Cactus for his work and other work, and then investigate alternatives necessary. And I have a final thought here. So, I think the state that we're at with this development is really in the early state of where the CMB detection was. Between 46 and 64, there were various papers predicting there was a microwave background. And they predicted that the temperatures range from below 20 to 45 Kelvin. And one paper predicted you could detect it. Ironic, it's kind of what we're saying as well. And then in 1964, on a totally unrelated subject, Arnaud Penzias and Robert Wilson measured an unexpected radio noise. And they looked everywhere for it. They thought it was New York, they thought it was pigeons, and they thought it was everything. And they, at one point, just concluded it wasn't. It had to be something else. So they published a paper on it, and a gentleman by the name of Robert Dickey identified it right away. He said, I know that's the CMB, that's the cosmic microwave we've been predicting for 20 years. What that did is it helped refine the models, because we were estimating less than 20 to 45. Well, now we know it was 3 Kelvin. And the rest is history, as they say, because after that, about 10 years later, COBE was developed. That was the first satellite to look at the cosmic microwave background. And it wasn't launched until 1989. So almost 50 years between the first thoughts of it and when they finally sent the satellite out there to look at it. So really the question is, when and where will the Bell Labs moment happen for this gravity wave spectrum as well, the gravity wave background? I think that's all that's needed. Is once you have a smoking gun to tell you that, hey, these gravity wave guys weren't off their rocker. They actually had an idea that is plausible. And what we hope to do from that is once that moment happens and someone identifies it, we go back and refine the models and change our 20 Kelvin to 40 to 3 Kelvin and tune our models and get better approximations of inflation. Here are our known Penzias, just to show you. And then here's WMAP, which was the latest satellite sent up after COBE, which did some really good work looking at the microwave background. So I'll leave you with those final thoughts. Thank you for your time, and any questions? Yes, sir?
Any possibility of this gravity wave line to...
It's a good question.
Yeah, I don't think so.
It's popping in my head when I was
Well, the only thing I can think of, the short answer is I don't know. But the only thing I can think of is maybe if they can tie it somehow to the vacuum energy of the universe, you know, since there's something going on there with virtual particles and so forth.
Yeah.
Maybe if they can tie that there to energy creation out of nothing, maybe it might assist that. But yeah, I don't know.
getting energy from space as you go.
Okay. Other questions?
Yes, sir.
I studied non-Euclidean geometry a little bit, and the way that was suggested back then for determining whether some space was flat or not, to measure a triangle, if you want some space that contains volume, you probably want tetrahedron or something, but anyway, you measure triangles and see whether the sum of the angles of the triangle were 180 degrees or some other number, but you have to have observers way, way far away. And you also have problems with simultaneity and stuff like that, which maybe you guys want to solve, I don't. But I get the idea that flat universe means something else now, and there's not stationary observers and measuring angles of triangles, and I don't know what it means. Can you explain what it means and how you determine whether or not?
Yeah, what the shape of the universe winds up correlating to is the fate of the universe, how much matter is in the universe. And then if the shape is flat, or if it's spherical, determines how we're going to wind up. In other words, if it's a runaway universe where matter dies, radiation dies, everything goes dark, we have a heat death of the universe. Or if we wind up doing the big crunch, as they say. Or if we just keep expanding and then something pulls us back and we just stay in this pattern of acceleration and deceleration. Let me see if I can answer it another way. Through the research, they've determined that the shape of the universe has to do with the matter in the universe. So that's why it's turned into that discussion.
Okay, I've heard the statement that the universe is flat, but I can't imagine how you would determine it.
Well, it's that.
Right.
Essentially, the way they determined that was actually looking a lot at this cosmic microwave background radiation and kind of fitting it against theory and about where we are in terms of the critical density of the universe. So they kind of, if you, it's a lot of mathematical calculation to get to that, because you literally can't send somebody out, you know, a billion light years in that direction and a billion light years in that direction and do a measurement, because, you know, it takes forever, literally. So what you do here is, if you look at this cosmic microwave background radiation and you look at the anisotropies in it, then you fit that against your theories about how you got these anisotropies and what they meant, and how long it would take them to collapse through certain effects. And you can tell from that what the density should have been, and, you know, how much dark matter there was, and how much of anything there was. And based on that, that's how they kind of determined how close we are to this critical density. And from what they found is that we're really close to it. Except now, what we thought was living in a flat universe is actually kind of more like that saddle-shaped universe, a little bit. But it's so close that you can't. It's very difficult to even tell the difference.
Well, and going back to what you stated, it's tough to see, but there is a red triangle on all these figures.
Well, yeah, but
And that is exactly what you were talking about.
like you said, that's just not feasible, and that's the only way I ever heard of doing it.
Right.
There is a much more complicated way, which
But you
probably
can calculate the geometry from the mass energy density using Einstein's equations. So you can, instead of actually measuring the geometry, you're calculating the geometry.
Right, and that
that
gets...
assumes you know a lot about where the masses are, and you may know quite a bit, but I'm a long way from everything. I don't think dark matter is understood. I don't think dark energy is understood. I don't know how you imagine it, how you can imagine you can do that.
Hey, you could imagine doing what?
How you can imagine that you can determine the density of mass energy when you don't really understand what dark matter is.
Again, you don't have to understand what it's made of in order to look at the cosmic microwave background and do a calculation from that. Because essentially, at a certain level, it doesn't matter what a ball's made out of, you still can understand a ball. And so, same thing with dark matter, dark energy. You don't have to understand exactly what they are and what they're made out of, you can still measure their density. And that's all that is coming from is a big density measurement.
Yes, sir.
Your work, you're talking about numerical analysis, and you explain the numerical method in the steps to what were you solving for? Were you using the Einstein equation? And what were your results?
Well, yeah, this chart here were the results. And basically all this was is a solution to, go back a few pages, to this equation right here. And to get that equation, well, and then also some adjustments for redshift afterwards. But to get this equation, we had to solve these mode functions, which then incorporated, pretty much it did not use Einstein's equations, even though the theory was developed out of all of that. It just used an assumption on the behavior of the gravity wave equation being similar to a 1D harmonic oscillator. That's what the assumption was there. And the thing that really had to be determined was this effective potential. And the theory did a good job of putting that together for us. And with some simplifying assumptions here, we get these solutions to that gravity wave equation, the G on the other page. This guy right here. To this differential equation, that's the solution here. So having these Whittaker functions is a numerical technique for that, which, to tell you the truth, it's been 3 years. I don't remember the exact details behind it, but it was a little more than Taylor series. It was a little more complex than that, but along those lines. It was a small step size. And that's how they solve for the Whittaker functions there. That answer your question? Or?
Sure.
How long did it take you to code it?
It didn't take me that long because a lot of it was ready. So.
What made this your contribution?
Oh, yeah, it was about 2 semesters plus a summer, something like that.
Yeah, about that.
Yeah. Yeah, the numerical side it was actually pretty nice to find most of the components there already. But going through the theory and understanding it and putting it into a form we could understand and use was what took a lot of the time. MATLAB, yes. Yes, sir?
With regards to the redshift, wavelengths grow in direct proportion to the expansion of space-time, or is it some fraction of that?
It's directly related. It's just based on really the scale, the ratio of the scale factors. How they change is how that wave will change.
Imagine a wave is oscillating, and then as you stretch out the space, the wave itself stretches.
Probably coupled to the background.
It is the background.
The picture that really impacted me as I was preparing for this was this one, which we may still be on a very curved universe, going back to your discussion or your question. But at least for us, we don't know it. And we've inflated so fast, we may not know that the real shape of the universe. We just see everything pretty much close to flat around us, like we're in a really big shape or sphere or something curved. So that was just something interesting to point out, that there may be a lot more universe out there relating to the gentleman's discussion of of dark energy, dark matter, that we are just not aware of right now. So, any other questions?
Why did you model gravity wave as a one-dimensional?
Yes,
Why did you model?
1D. Yes, just different polarity, but that really just changes sign in the equation. It was not as a vector or anything like that. No tensors, just 1D. Yes, sir.
Can you clarify something for me? You mentioned bang and got off into the rest of the expanding.
No. And I should have been clearer. Really, this whole model is the Big Bang. What happens is, if this top line here is let's say, is the size of the universe, and if you go backwards in the Big Bang, it just keeps going like that, linearly. And so what this phase does, with this inflation phase that was added, is I hate to say, but it's kind of a not a fudge factor, but a catch-all to say, oh well, there must have been some phase that between the quantum or the big plasma changing to the size at some time later on, the big step function. But go ahead, sir. Go ahead. Sorry.
Something that happened during the Big Bang that's lived during that.
Right.
I see.
It adds to it. It doesn't say that it doesn't exist. It adds a key component that was needed to make these other problems that I mentioned go away. That's what it was. Yeah. And then we had this, and we're done. It makes sense again.
Yeah, without that, the universe doesn't work right, because you never get back to a singularity. I say the universe is just too young.
Yes, sir.
What's your reference for your gravitational wave spectrum?
Good one. I'll tell you to look at the paper, but I can go ahead and pull up the paper if you want. I have it right there. Our paper was published in the Classical Quantum Gravity, and we have, I think it's about 15 references. Which one particularly were you interested in?
The gravity wave spectrum.
Oh, the spectrum, that was mostly from Grischuk, LP Grischuk, and also Zhang produced one, and I think Alexander and Martin talk about it. And
They talk about it, but they didn't use the Grischuk.
Right. And I can provide those for you in a second.
I was interested in the visuals.
Yeah. It's tough to see this at first. It's tough to understand what they're really getting after here when you're not used to dealing with it. I'm an engineer by trade, so I'm used to gyros and elevons. I'm not used to this stuff. But those sources are good. They'll explain everything you want to know.
Yeah, any other questions? All right, let's thank our speaker again.